sun, and then it sort of gets the magnetic field and curves around. A few of them will come near the surface, near the poles where the magnetic field lines come together, and that's responsible for the aurora borealis, the northern lights. But the same can't be true on Mars. The Martian core does not have this type of turbulent convection, so its core is apparently relatively unstirred. This produces no appreciable magnetic field in the present day, which allows the solar wind to directly impact the Martian surface. We'll come back to some consequences of this later. Another consequence that's important for human spaceflight is that the presence of solar wind radiation on the surface makes the radiation environment rather unfriendly for human beings. So that's the core. Now moving up to the mantle. This is most of what comprises a planet. It's about 70% of the mass, and it's all solid rock. And specifically, it's this type of rock called peridotite, which is this green rock here. And this is also the same rock that is found in Earth's mantle, which is why we have a picture of it. This is not a meteorite. This is a rock that was excavated by a volcano. And the difference between the Martian and Earth mantles is that the Martian mantle contains almost twice as much iron as the mantle of Earth. This might be confusing because I just said the iron was in the core. In fact, there are two types of iron. So iron is a chemical element, and it is found in the universe in various forms, two of the most important which are metallic iron, which is a metal. It creates alloys with other metals, and it's silver gray in color. As I said before, it's not present on planetary surfaces generally, only in the core. And then there's another type of iron called ferrous iron. Iron is green, it's a component of rocks. And so if you've ever seen a green rock, it's likely that was colored by the presence of ferrous iron. In particular, in the mantle, it's found in this mineral olivine, named after the olive green color, which is the primary mineral, and which will come up later in the talk as well. Mars has a lot of ferrous iron in the mantle, and because the planet only has so much total iron that it must distribute between these two types, the fact that so much iron is in the mantle means that relatively less iron is in the metallic core, which is an important clue for some details of Martian formation. And finally, the last and smallest layer of a planet is also the one that is most familiar to us because it's on the outside, which is the crust. This is a negligible portion of the planetary mass. And it's, in the case of Mars, only a few tens of kilometers or tens of miles thick. This is, as I said, not very much of the planet as a whole, but it's what we can see. So when you take a picture, what you're observing are rocks on the crust, which are a different type of rock than the rock in the mantle. So this is the basic structure of a terrestrial planet. You might be curious how we know any of this, especially for Mars, seeing as the crust is 40 miles deep, and the deepest hole ever dug on Mars is about 4 inches deep. There's a few sources of data that we use to elucidate what this internal structure looks like. Just very briefly reviewing them. One of the most recent and important ones is the InSight mission, which was a lander with a seismometer. This is also the lander that dug the aforementioned 4-inch hole. And this, because it has a seismometer, it can pick up vibrations from Mars quakes that travel through the deep interior. And this allowed us to do things such like measure the size of the core for the first time. Additionally, there are Martian meteorites. So these are rocks that were in the past ejected from Mars by asteroid impacts and eventually collided with Earth. They are the only rocks we have from any other planet, and so it's fortunate that we have them. These are how we know pretty much anything about Martian chemistry. If you see here, this particular meteorite, which is called Nakla, actually you can see it has the green olivine mineral, which is the major component of the mantle. So this tells us a lot about what the mantle is like. And then finally, we have Mars orbiting spacecraft, like the Mars Reconnaissance Orbiter, shown here. If you're in space and you're orbiting a planet, you can do things like measure the entire density of the planet or the entire size of the planet. And also you can take images of the surface, which are very, very important, as now JJ will speak to you about.
Hello, everyone. Hopefully everybody could hear me. I'm JJ, and I guess Matt have introduced us the inner workings of the planet Mars, and we will explain a little bit later why the internal structure and the composition of the planet are connected to the question how Mars got its water at the first place. Before we get into that, I guess I just want to give you a brief tour of the surface of the planet. So I guess in the next 5-10 minutes or so, I will be able to finish part one. I'm going to introduce you some key geological features of the Martian surface that might have been associated with water histories of the planet. Next slide, please. So before we travel to Mars, I think let's look at our home planet Earth first. So this image in the middle that was taken by Apollo 17 when the spacecraft was traveling to the moon. So the name of this picture is called Blue Marble Earth. The blue are the oceans, which is kind of the largest reservoir of liquid water on our planet, planet Earth. And the marble part is the Antarctica you see at the bottom of the image, and kind of the heavy clouds covering the entire southern hemisphere. And the green are the continents. And specifically, I guess in this picture, the continents you are seeing are the African continent, and you also see this kind of Arabian Peninsula on the horizon towards the northeast. The major difference between Earth and Mars is surface water. Liquid water on Earth makes life as we know it possible. So in addition to this blue marble Earth I'm showing here, there are also pictures I'm showing of people playing soccer, ash tree, glaciers on the right, and open water, which is, I think for this picture is the Atlantic Ocean. And so the habitable environment and water and life is what make our planet Earth unique. So Earth is a planet with a lot of water on its surface. But what does Earth looks like without water? Next slides, thank you. Here is a completely different view of our planet Earth. This one is without water. So we call this type of map a topographic map of the Earth because it shows us the shape of the Earth's surface. The blue color in the map now is the bottom of the ocean. I kind of circled some of the areas within the blue box. And the bottom of the ocean could be as deep as more than 10 kilometers. And there is a kind of the cross sections of the ocean bottom I show on the lower left of the slides. And the green to red colors in the map are the land, and the mountains on the Earth can be as high as more than 8 to 9 kilometers. I'm also circling a small box. I'm also outlining a small box in the map, and I think that's the Mount Everest. The color changes in the map from blue to green, then to red, indicates different elevations from oceans, land, to the mountains, which is kind of the red, white color. This kind of topographic map gives us a better sense of the distributions of the elevations across the planet. So the reason I want to introduce this topographic map for Earth because it's going to be very useful when we look at a different planet. So what does Mars look like? Next slide. And in the middle of this slides, we have a global view of Mars. And at the bottom of the slides, there is this panorama, which is a picture of the Martian surface taken by Curiosity rover, where NASA sent to Mars in 2012, I think. So unlike the blue oceans and green continents we saw on Earth, the surface of Mars is red, cold, and barren. Next slide, please. And something very similar, I guess, between Mars and Earth is both we kind of divide the planet into northern hemisphere and southern hemisphere. In Earth, northern hemisphere, we have the United States, and southern hemisphere, we have Australia, and that's how we divide the planet into two parts. The northern hemisphere of Mars has lighter colors in this picture. compared with the southern hemisphere of the planet. It is because the southern hemisphere of the Martian surface is much older and is covered with a lot of craters. Next slide, please. And you may also notice there are like some white patches near the polar area of the planet Mars. They are ice caps. They are primarily made of ice, which is a solid form of water, H2O, and also dry ice, the solid form of CO2, carbon dioxide. Carbon dioxide is a greenhouse gases that we become increasingly familiar with because it drives global warming. On the Earth, the surface of Mars can be so cold that 30% of its atmospheric CO2, carbon dioxide, freezes at its ice caps during the Martian winter. So from this view of planet, this global view of Mars, you may think Martian surface is pretty uniform, and it's actually just the opposite. Next slide, please. So now I'm showing a topographic map of Mars. On Earth, we have a global ocean basin with low elevations and scattered patches of continents with higher elevations and mountains. Mars looks quite different. The distributions of elevations is kind of divided along the equator between a northern hemisphere and southern hemisphere. The northern hemisphere in this map, it's the upper part of the figure, it's flat plains. We color that in blue. And the southern hemisphere is highlands in yellow and plateaus in red. And the relative elevations of the southern hemisphere is quite high. So within the southern highlands, which is the lower part of this map, we have high mountains like Olympus Mons, which is I also highlight. It's one of the little dot, white dot on the left part of the map. The Olympus Mons is the highest mountain in the solar system. It's 2.5 times the height of the Mount Everest, which is highest mountain on Earth. At the same time, we have a large impact basin, Hellas Basin, which is something I also highlighted in the map. It is 1,500 miles across, which is about the distance between Seattle and Houston. So it's quite big. Next slide, please. So Hellas Basin is not the largest basin on the surface of Mars. The largest one is on the polar area, the North Pole of Mars. It comprises 1/3 of the entire northern hemisphere and looks kind of like the ocean basin we saw on the Earth. So I'm already kind of alluding the answer. The northern basin, the polar area of the Mars North Pole, it is also where the ancient Martian ocean might have been. Next slide, please. So Mars have many impressive mountains and canyons. Olympus Mons, I have already mentioned, and Sarsis Montes are also a series of 3 volcanoes on Mars. They are highest mountains in the solar system. We also have Valles Marineris, I'm showing on the right side of the slides, which is one of the deepest canyons in the solar system. Both features associated with Martian water history. The eruptions of those volcanoes will release a lot of water to the surface. And the Valles Marineris, this type of canyon, could have been carved by the liquid water activities in the past. Obviously, most of those waters have already gone by now. Next slide, please. So today, a majority of the Martian water resides at its polar ice caps. Here is kind of a close shot of Martian North Pole. This is a processed image of the Martian North Pole based on the orbiter image and the elevation data. But I kind of give a sense of what Martian North Pole looks like. Next slide, please. So the ice here on the North Pole is about 2 kilometers deep and have a volume equivalent to almost half of the size of the Greenland ice sheet on Earth. I'm also showing a small picture of Earth with a Greenland ice sheet at the lower left. Next slide, please. So in this slide, there's another photo of North Pole of Mars, but taken from a different angle by Orbiter. So Orbiter is a spacecraft. That flies around the planet. I just want to point out that this image is a real image of Mars. It's not a mock-up. Recently, a European Space Agency has this orbiter called Mars Express. It has found water, liquid water flowing underneath those ice layers in the polar area using its radar, which is kind of the brightest area in the figure on the right. This is one of the most recent evidence suggesting long-term flowing liquid water existed on Mars. Next slide, please. So from the satellite images, we note that the majority of the water on Mars now kind of stays in the polar ice caps. Then we might want to ask the question, how much water is actually in them? Earlier, I was comparing the water stored in the ice sheet in Greenland on Earth with ice caps on the North Pole of Mars. If we use the Greenland ice sheet again as a unit, the water stored in both the North and South poles of Mars would be about 1 to 1.5 times of the water in the Greenland ice sheet. Next slide, please. Of course, planetary scientists do not use Greenland ice sheet as a unit for water on Mars. Instead, we use a unit called global equivalent layers, in short, GEL, meaning the depth of a water envelope you will get when you spread the water evenly across the planet. So if we melt all the ice on the Martian surface today, it will produce a 20 to 30 meter global equivalent layers of water. Next slide, please. So to summarize kind of this part one, Matt have talked about the internal structure of the Mars and how we know it. And after that, I give this brief overview of the surface of Mars and how much water it has today. Now we will take a break, and in the next session, Matt is going to tell you about how Mars got its water during its formation, I think in a few minutes.
Great, thank you so much. Are there any questions from the audience on the first section? Maybe I can ask one while people are thinking of them. I was wondering, as you're like describing these polar ice caps, I don't know like for how long we've known about these, but do we know how fast they might be changing? You know, like I always think about like as the Earth ice caps that are melting and things like this. Do we know if the like similar types of changes are happening to the ice caps on Mars?
I'm actually not an expert on ice caps on Mars, and my understanding is there is we can break this into two categories. There is this long-term change, which is on the scale of billions of years. And in that sense, we are losing water we are losing water from Mars, but we also have this short-term variations in the ice caps. If we really look at Mars within 5-10 years, and you can see the season, even just within one Mars year, which is 2 years of 2 Earth years, you can already see the change in ice caps. And maybe in the summer, we'll have much less ice on the North Pole, and in the winter, we will have more. There is the seasonal changes in the ice caps, but for a much shorter time scale.
Interesting. Mary Brennan's also asked in the chat if Mars and Earth are the same age.
It's a little bit hard to answer how old something is. That's essentially a giant pile of stuff. So if you have a giant pile of sand and you keep adding more and more sand, how old is the pile? Is it when you started adding sand or when you finished adding sand? So one way to answer the question is that everything in the solar system is about the same age, which is about 4.5 billion years old, which is the age of the sun. There's reason to believe that the formation time scale, so how long it took to grow Mars and to grow Earth, is a little bit different, so that Mars might have grown a little bit faster. And it's something we'll get into in the second part. But on the scale of billions of years, the difference between Mars and Earth is not very large. So you can imagine both of them being about 4.5 billion years old, which is the same age as the sun and everything else in the solar system.
Great. Maybe let's get started with the second part. I just put in the chat a link to a handout that has some definitions of different terms that you might hear, as well as further information if you're interested. So feel free to check that out and follow along. And take it away as we go into part 2.
Okay. So the second part is going to be about the origin of Martian water. And first, I'm going to address a question that you might have had when you were listening to me talk about the structure of Mars in the previous part, which is, what does any of this information about the Martian interior have to do with the presence of Mars water? So if there was an ocean on the surface, why does that have anything to do with the composition of the core or the crust, for example? And the answer to this is related to the fact that planets are old and their formation is very complicated. So they gather most of their material very early in the solar system history, and all of that material evolves over time, and especially is sensitive to the conditions of their formation. So the formation of the oceans on Mars is coupled with the formation of the crust, the core, and the mantle. Which hopefully will become clear over this part. To begin with, let's talk about water in general. So I'm sure all of you know that water is also referred to as H2O. This means that it's a molecule made of 2 hydrogen and 1 oxygen atoms. And hydrogen and oxygen are 2 of the 3 most common elements in the solar system, and also in the universe at large, for that matter. If you think about the solar system in terms of elemental abundances, almost everything in the solar system is hydrogen and helium, which is almost all inside the sun, and a little bit of oxygen left over, and then every other element is a very, very small fraction. So in the early solar system, when all this stuff was mixed together and forming, there was abundant material to create water. So water would have been very common in the early solar system environment. Another important thing to keep in mind moving forward is that there is no liquid water in outer space. The pressures are too low. So in outer space, water vapor transitions directly to solid, which is water ice, at around -125 degrees Celsius, so much colder than the freezing temperature of water on the surface of Earth today. So the early solar system was formed from a cloud of this type of stuff, which all gravitationally attracted towards each other, collapsed until the middle was so dense that it ignited nuclear fusion and became a star. When the sun turned on, it either consumed or blew away, with the solar winds that I mentioned earlier, all the material in the center of the cloud. And what was left was this sort of donut-shaped disk of gas and dust. This is called a protoplanetary disk because the planets are formed within this cloud. And the way they do that is by condensation of material from the disk. So as things begin to solidify, they begin to gravitationally attract and create larger and larger piles of stuff, which eventually become the planets. As this happens, the planets start to orbit the sun, and then this phenomenon occurs where the planet will sweep up everything that is within its orbit. So it'll gravitationally attract all of the clouds and all of the dust that is nearby it as it moves around in an ellipse. And so a planet like Earth will sweep up a smaller portion of the disk, and a larger planet like Jupiter will sweep up a larger thing. And these gaps are actually visible. So until very recently, this idea was entirely theoretical, but it has lately become possible with radio telescopes to actually image these protoplanetary disks, which is what this image shows. This is a star system called HL Tau, and it is currently in the process of forming planets. So there's a very young star with a disk around it, and you can see that you can make out the rings in which individual planets are forming and gobbling up the material in their indigenous orbit. Another interesting thing that you can see from this image is that the disk is not homogeneous. So the color of the disk is changing from the inside to the outside. This is obviously not a true color image, but this gradient of color from very bright in the center to darker on the outside actually reflects the gradient of temperature in the disk. So as you might expect, the material very close to the central star is very, very hot. But then as you move further and further away, it becomes much colder. And at some point, this disk, which remember contains a lot of water vapor throughout, because water is such a common material in the early solar system, at some point becomes so cold that ice begins to condense directly out of the disk. And we call this the snow line. So all of the disk inside the snow line has no ice available. All of the disk outside the snow line does have ice available. And this has a very big impact on the formation of planets in either region. In fact, if we go back to or if we go and just look at a snapshot of planets forming in different regions of the disk, you can sort of see why this happens. So in the inner disk, if you're this planet here, you're carving out your path, and you're only able to grow by attracting material that is capable of being solid at these very high inner disk temperatures. So these are things like metal, which eventually goes and forms the core, and rock, which eventually goes and forms the mantle. And then contrary, in the outer disk, if you're a planet very far away from the sun, you're condensing where the disk is cold, you're able to grab ice that is condensing out of the disk. And because there's so much water, the amount of ice available outside the snow line is very, very large. And so planets out here are able to gather up huge quantities of material that would not be possible in this sparser part of the inner disk. If in between those two cases, you're a planet that's forming near or at the snow line, you're gathering still mostly inner disk material, so iron and rock, or metal and rock, but you also might be able to gather some icy particles that have condensed beyond the snow line and then sort of drift inwards to join your growing planet before they evaporate again. Now, if we think about the consequences for the architecture of the solar system as a whole, it's suddenly now makes a lot more sense why there's this very dramatic divide between the inner terrestrial planets and the outer gas planets. So the snow line, as far as we know today, would have fallen directly, in between the present locations of Mars and Jupiter. And this means that Jupiter and the planets further out were forming in a region where there was a ton of water available, which they were able to gather and grow very, very large. Whereas the terrestrial planets were in a much sparser region, so they only had rock and metal, and there's not as much of this as there is of water, so these stay small. Further sort of corroborating evidence for this can be found by looking at the material in this gap between the planets, which is where the asteroid belt is. If you take a random asteroid, it's sort of a toss-up whether it looks more like inner disk material or outer disk material. So the largest asteroid in the asteroid belt is called 1 Ceres, and it's a mixture of ice and rock, whereas one of the other very large asteroids, 4 Vesta, is a mixture of rock and metal, a lot like the Earth. So Ceres kind of looks like outer disk material, rich in ice. Vesta sort of looks like inner disk material, very little ice. And these are right in between where the snow line would have been. So what does this mean for Mars? Because Mars is definitely one of those terrestrial planets. As we saw, it's small, it's made of rock and metal, and it's fairly close to Earth. However, it is also the planet that's closest to the location of the snow line. And there's reason to believe that Mars might not have always been where it is today. So if you look at an image of the solar system today, you probably know that there's not a currently existing protoplanetary disk. That cloud of gas and dust was eventually either consumed by the planets or blown away by the sun early in solar system history. And once that happened, there was a period of chaotic migration and collision of these planetary bodies. So they might have moved to different orbits, or they might have hit into each other. In fact, one such collision between Earth and a body about the size of Mars is believed to have formed the moon. So we know that Mars-sized bodies were moving around during this period. And in fact, it's possible to do computational simulations of the dynamics of these bodies. So you can do simulations of this chaotic period and try to predict where the planets were most likely moving. And when you do this, actually, you find that you very rarely form Mars near its current orbit. So these are the current orbits of the planets. And you can see that very few of these simulated Marses actually match the current orbit of Mars. If you want to match the current orbit of Mars, you almost always end up with a planet that's not the right size. So to match the actual properties of Mars that we see today, it's much more likely that you form Mars closer to the snow line, further out in the solar system, where it would have been able to gather some water by condensed ice, and then have it migrate inwards later. This isn't total speculation because there is some circumstantial evidence that suggests that Mars actually accreted wet, or accreted means that grew. So that Mars grew in a location with a lot of water. And this goes back to the difference between the types of iron, which I mentioned earlier. So if you're a single atom of iron, the choice between being part of iron metal or being part of ferrous iron is essentially related to how much oxygen or how much water is in your environment. So the fact that, as we learned earlier, Mars's mantle contains almost twice as much ferrous iron as the Earth's mantle does indicates that Martian formation occurred in an environment where there was enough water to force a large portion of the total iron to be in the mantle rather than in the core. This cartoon sort of illustrates that. If you have a high water forming environment, you end up with a lot of ferrous iron, so a larger mantle, whereas if there was no water in that formation environment, much more of the iron would be in the core, which is consistent with the observed density and size of the Martian core. Furthermore, there's yet another type of iron that I haven't mentioned previously, which is ferric iron. This, instead of being green, is rust colored. In fact, that's what rust is, it's ferric iron. And the reason that if you take a piece of iron metal and you place it on the surface of the Earth and it rusts, it's because the Earth's surface is a very, very high oxygen-rich, water-rich environment. So it rapidly reconfigures iron available into this rusty red color, which of course is the rusty red color associated with the surface of Mars. So the entire surface is covered with this layer of red ferric iron-rich dust. And this indicates that beyond even the iron that was available in the mantle, the surface of Mars would likely have been very water-rich at some point in order to rust all these rocks. So let me just go through and sort of summarize the history of Mars. So this is the consensus view of how Mars formed and developed up until the point where it had a large amount of water. So this is going to be sort of a timeline in dates after the formation of the solar system. So year zero here is going to be 4.5 billion years ago when the sun turned on. In the first 2 million years of solar system history, Mars begins condensing out of the protoplanetary disk. It was likely close to the snow line, so it gathered a bunch of material, which was mostly rock and metal, but also included substantial amounts of ice, so much more ice than, say, Venus would have had. All this stuff was sort of homogeneously mixed together in this sort of primordial mixture here represented in dark green, and the pile gets bigger and bigger as it gathers more and more material. Eventually, the center of that pile gets warmer and begins to melt, forming magma, and eventually the whole planet becomes molten. By the time the whole planet melts a few million years into solar system history, the protoplanetary disk has dissipated. It's been consumed or blown away. And now we're in the chaotic period, which is when the planets were migrating and colliding with each other. During this period, Mars probably migrated from somewhere closer to the snow line towards its inner solar system home, where it is today. Along the way, it likely experienced large impacts with smaller planets and asteroid-like bodies. And this helped it remain molten. So once you have a planet that's entirely melted, you can start to separate based on density. So the metal that was in the primordial mixture of Mars is the densest substance, and it sinks and forms a core. Whereas the magma, which is liquid rock, is a little bit less dense, so it rises and will eventually form the mantle. So a lot of the iron goes into the core, but not quite as much as would have gone in on Earth, because remember, this primordial mixture, which is now melted, contained a lot of water. So much of that iron ends up as ferrous iron in the mantle. Another important thing that happens here is when this core is forming, it's stirring around because it's so hot. It's very turbulent. And this turbulence drives the creation of an early magnetic field, which is represented here with the pink lines. After about 10 million years in solar system history, Mars is at its now modern orbit, and it begins to freeze. So this magma ocean that was covering the surface begins to solidify from the inside out, creating the solid mantle. And as this is happening, the water, which was trapped in the magma, begins to sort of bubble out and form this very thick steam atmosphere. This steam atmosphere is protected from the solar wind because there is still rotating turbulent liquid metal in the core driving planetary magnetism. So there's still a magnetic field protecting this steam atmosphere. And then the last stage I'm going to talk about will take us up to about 4.1 billion years ago. So about 400 million years after the formation of the sun. And this is sort of the warm, wet, habitable Mars. This is a situation where the mantle has entirely solidified, but maybe a few last little vestiges are molten and continue to breathe gas into the atmosphere and form the volcanoes, which are seen on the surface of Mars today. A lot of that original thick steam atmosphere has condensed and rained out to form liquid water on the surface of Mars. But there's still probably liquid water in the atmosphere as well. At this time, the core is still circulating and still driving a magnetic field. So this whole situation is still protected from the solar wind. So this is where the habitable Mars that you might have heard of comes from. It's this early Mars, which has solidified, but still maintains active volcanism, so active geology. Has liquid water on the surface, water vapor in the atmosphere, has a magnetic field, and all in all, it's a pretty wet surface environment. So what went wrong? What happened in the last 4.1 billion years to get us from that wet, habitable Mars to the dry, cold, largely waterless Mars that we see today? That's what we're going to talk about in the next part. But for now, we'll take any questions you have about part 2. I don't know if our moderator is here. Yes, she is.
All right. There's one question in the chat from Katrina Velder asking if gas planets are actually ice planets.
Sort of. There's a couple of subtleties here of gas planets that I haven't mentioned. So Saturn and Jupiter are significantly larger than Uranus and Neptune. And those last two, Uranus and Neptune, are often called ice giants because they are largely liquid water or largely gaseous water. Whereas Jupiter and Saturn contain a lot of water, but they also contain a lot of just pure hydrogen gas, which they actually collected directly from the protoplanetary disk. So sort of the story there is that they started gathering probably water and rock and metal, And Jupiter and Saturn got so big that their gravity was sufficient to trap hydrogen gas, which requires something really, really large because hydrogen is so light. So the sun is really big and it can hold on to a lot of hydrogen. But for example, Earth is nowhere near big enough to hold on to pure hydrogen in the atmosphere. And in fact, even Neptune isn't big enough. But Jupiter and Saturn sort of gathered enough ice originally that they exceeded that threshold and were able to hold on to protoplanetary disk material as well, instead of just the condensates.
Yeah, I guess one small note in addition to what Matt have already said. So to a planet, ice is a totally different concept. To us, ordinary person, daily life living on the surface of the Earth, ice is something that will freezes at 0 Celsius. And it's you could have the same material, water, in a planet and in the interior of the planet. In that case, you will have the solid form of water, ice, at a much higher pressure as well as at much higher temperature. So let's say you could have ice at 70 degrees Fahrenheit if you compress it to a higher pressure. So some of the ice we are talking about for those gaseous planets in the interior of those gaseous planets are in the solid form, but are not necessarily have a cold temperature because the force of pressure. So water could become ice at a large range of conditions, pressure and temperature conditions, not necessarily just limited to the conditions for the surface of the Earth.
We have one other question from Sebastian, who's wondering where the water on Earth comes from and if Earth followed the same path as Mars to get its water.
So probably in the sense that it probably gathered water from material that was sort of colliding with it. We're not here to talk about the origin of Earth water, which is somewhat controversial and I'm not an expert in. But in general, it's accepted that most of the water on Earth came from large, like asteroid type bodies, which collided with Earth rather than being primordially gathered from the protoplanetary disk, the way that we believe Mars might have been. But this is like a topic of active research. It also might be worth pointing out that Earth is a lot bigger than Mars and probably experienced far more of these large impacts during its early history than Mars did, including the impact that formed the moon. So it had a much larger sort of series of big growth steps when it could have gathered a lot of water all at once.
Yes, one of the things Matt mentioned in his part is actually really relevant to this controversial question about the origins of water on Earth. I think that element is that aspect is the snow line in the protoplanetary disk, because when Matt was defining the snow line and how the community defined the snow line is where water condenses, and that's kind of the division between snow within the snow line and beyond the snow line. And I think the active research Matt is mentioning is there any need to redefine the snow line, really to incorporate Earth into the water-rich region as well? And the way to kind of shift the snow line inward to this early solar system is not thinking of water as liquid water. It's actually thinking of water in some solid form. For instance, water could be present in a common mineral we know, talc, which is have water in its structure. So when a protoplanetary disk is cooling, even though we have not cooled enough to form liquid water, we might form some kind of a rock, some kind of minerals that contains water within the structure. And those are the materials that are available in the orbit of Earth at that time. So it's possible Earth was made of those materials, not necessarily with liquid water, pure form water, but with some type of rock that are actually enriched in water.
That's really interesting. Are there any other questions on part 2? Okay, perhaps let's just take another short break. Let's do 3 minutes this time, and we'll start part 3 at 7:35. All right, so let's go on to our last part and learn about how Mars lost its water.
I think I will be doing the last part, and I will ask Matt to help me to switch the slides. So in part 2, Matt have already told us that the building blocks of the planet Mars might have been very water rich, and those materials would have brought tens of thousands meters of water to the Martian surface. But if you look at the polar area of Mars today, we only see 20 to 30 meters global equivalent layers of water on Mars. You might start wondering, what did all those water go? To tell kind of this complete history of water on Mars, we have to go back to when Mars first solidified as a planetary body, and when Mars was just formed. So next slide, please. So when Mars left its magma ocean state and formed its solid crust, the surface looked quite hellish. There were a lot of large volcanoes, and those large volcanoes were releasing oceans of water onto its surface. This process probably continued for at least 500 million years. We can see similar events on Earth today, but on a much smaller scale. In this slide on the right, I'm showing volcanic eruptions in Iceland in 2014. And there were a lot of clouds in the picture, and the clouds you see here contains debris, water, and other types of gases. This is similar to how water was outgassed from the interior of Mars at its formation. The water vapor in those clouds would then condense to form liquid water on the early surface of Mars. Even the majority of the first water on Mars now was gone. There were actually a number of evidence on the Martian surface that suggests some past activity of liquid water. Next slide, please. So as we kind of alluded earlier, if Mars had much more water in the past, most of the water would have stayed in the northern hemisphere because the elevation is lower. The boundaries of the northern hemisphere looks like the shorelines on Earth somehow. And we have a photo of Pacific shorelines in California in this slide on the right. And the water was somehow once breaking upon the Martian shores in the distant past as well. On the left, here is a map of Mars northern hemisphere, kind of viewed from above. It's a North Pole. The black dashed boxes shows kind of different surface features I mentioned in the previous parts. I think one features I already mentioned is Olympus Mons, which is a very large volcanoes on the Martian surface. And the colored lines in this map shows all possible shoreline features on the Martian surface planetary scientists have identified in their research. The early Martian oceans could have been as big as the entire northern hemisphere, or it's actually much smaller and only limited in the polar area. Next slides, please. So the shorelines we just saw are not the only geological features that might have been associated with water on Mars in the past. I already mentioned this canyon, Valles Marineris. This canyon on Mars bears a lot of resemblance to the Grand Canyon of Arizona. The bottom right picture is an image of a Grand Canyon of Arizona taken from the International Space Station. It's very similar to the Grand Canyon. What I'm calling it the Grand Canyon of Mars. It's very similar to the Grand Canyon of Mars, which is Valles Marineris. And this big Grand Canyon of Mars could also be carved by water activity as well, which is kind of shown on the left from this perspective view. The Valles Marineris is also the largest canyon in the entire solar system. Just for the sense of the scale, the entire length of the Valles Marineris, it's about the distance between the west coast of the United States to the east coast of the United States. So it's going to be a lot of water if we fill the entire Valles Marineris with water on Mars at some point. Next slide, please. Other features on Mars, such as other features like delta-like fans, are also discovered on Mars. So in this slide on the left is delta-like features on Mars. So we think it's related to a lake delta, possibly carved by liquid water activities. And on the right, there is a picture of a lake delta in Louisiana on Earth. And just look at their shapes, they look really similar, almost identical. Those lake deltas are of particular interest to planetary scientists because the sediments and rocks in those lake environments could hold traces of ancient lives on Mars if there had been any in the past. Next slide, please. So this is a very dense slide. One of the NASA's recent mission was to land a rover named Perseverance near in Jezero Crater. Jezero Crater is thought to be like an ancient lake on Mars. And in the black box of this middle figure in the upper panel, we can see some delta-like features at the rim of Jezero Crater, which is a landing site of the Perseverance rover. Jezero Crater is an impact crater, but it might have been filled with water in the past, billions of years ago. So the right image on the upper panel is kind of an artistic impression of what Jezero Crater would look like if it was filled with water. The yellow dashed lines are indicating the boundary of the crater and also the boundary of the Paleo Lake. The blue box we saw here is kind of a river that goes into the crater lake and feeding water into the impact crater. And the delta-like features we saw today was originally where the crater lake and the river meets. In the lower panel, I'm just showing a bunch of photos about this particular mission. NASA sent it to Mars about 2 years ago. So on the lower right, I'm showing a picture of this Perseverance rover who is currently traversing across Jezero Crater as we are speaking. The moving part in the picture is kind of the high resolution camera it carries to look at stuff on Mars. And just a side note, I think this is the most fascinating part of this mission. In this mission, we also sent a small helicopter to Mars. And the name of this Martian helicopter is called Ingenuity. And it can take photos of Jezero Crater from above. And I think so far it has performed around 20 flights. And this is very exciting, and it's a milestone of our Martian exploration because this is kind of the first powered human-controlled extraterrestrial flight we ever have performed. So in the middle part of the lower panel, we see a photo of this Martian helicopter taken by the camera the rover took with him, and the blades of the helicopter is still moving and it's about to take off. On the left, we saw a photo of this rover, Perseverance rover, taken by the camera carried by the helicopter. And it's kind of cute to see those two kind of instruments just taking photos of each other on the surface of Mars. Next slide, please. I think this is a more serious slide about the science the Perseverance rover is doing. Right now on Mars, the Perseverance rover has been sending back so many fantastic photos of the Martian surface, and I want to only highlight two. So in the upper part of the slides, we have a photo of ancient layers of rocks. Inside the Jezero crater, near the delta-like features, I pointed out in the location map. It is in the location A. I also have this zoomed in photo of them, and those I think it's in the upper panel on the left, and you can see those layered features in the rocks. And those features might have been formed in the river delta by the water activities. So at the moment, the rover is driving uphill to get to the edge of the crater. The lower panel is kind of the panorama the rover have taken of at the rim of the Jezero crater in location B, indicated in the location map for the rover in the middle of the slides. One exciting thing is we are also collecting samples at the Jezero crater, and we plan to bring those samples back in the next decade. And those samples will give us a lot of exciting evidence of water histories on Mars. So now back to water, we know there had been more water on the surface of Mars billions of years ago, but what does the early Mars actually looks like with all those water? Next slides, please. So here again, it's a map of Mars today, and many of us now are familiar with this imagery of red Mars, dry, cold, and lifeless, waterless. I highlight some of those geological features, and I think we have introduced many of them in the previous part of the talk. I outlined the northern basin of Mars in yellow color. One type of the theories argue that the entire northern hemisphere of Mars was once a big ocean, one single big ocean. And I want to show you what Mars looks like if that entire northern plain is filled with water. Next slide, please. So I did some processing to that, digital processing of that Martian map based on the elevation data. And here is what the blue Mars with northern ocean might look like 3 billion years ago. There was this vast ocean colored in deep blue in the northern hemisphere. The land remains kind of above water are in the southern part of the planet, which is colored in green. Even in general, southern hemisphere is covered with highlands, and the elevations of that southern hemisphere is relatively high. You still have some regions like Valles Marineris, which is the largest canyon, can be filled with a lot of water, and you always have this Hellas Basin can also be filled up with water. So this is what the early Mars might have looked like in the past. And it looks blue, looks warm, and also could have been an ideal ideal place for life to begin and to thrive. Next slide, please. Of course, because we are talking about Mars, we have never been there, and it's also early Mars is a distant past. There are a lot of uncertainties still associated with early Mars, and one of the biggest uncertainty about early Mars is the climate. If the early Mars was warm and was able to keep water from freezing, the early Mars should look like the blue Mars on the left. And let's just call that a water world. And if the early Mars was rather cold, the vast amount of water would freeze into ice, and it stays in the plateaus of the southern highlands as becoming glaciers and ice sheet, like what you see in the Colorado Plateau, you see Swiss and French Alps. In that case, we lost our blue early Mars, and we would end up with a snowball Mars in the past instead. One thing I would like to highlight, though, is that no matter water was present in the liquid form or in glaciers in a solid ice form, all evidence kind of suggests that Mars surface had much more water than what we have on Martian surface now today. Next slide, please. So at the beginning of this part, I mentioned that initial volcanic outgassing gave Mars enough water to form rivers, lakes, and even oceans. The question now is how did Mars loses almost all those waters in the past 4 billion years? Next slide, please. So there are 2 ways people have proposed to solve this mystery. I'm kind of making a flow chart in this slide. The 2 water loss mechanisms are highlighted in the red boxes above and below. In the middle, the first one is water loss through atmospheric escape to space in the upper box, and the second one is water loss to the crust, to the underground, through forming hydrous minerals in the lower box. Next slide, please. So the water loss to space, it's the first theory scientists came up with to explain the missing water on Mars. Matt mentioned multiple times that unlike Earth, Mars now lacks a strong, long-lasting magnetic field to shield its atmospheric water from the sun. So the Martian atmosphere has a much more intense interactions with the solar wind. The solar wind, I guess I would define it here, is kind of a stream of particles emitted by the sun with very high energy. It is deflected by the Earth's magnetic field, but those solar wind is hitting Mars head on because Mars has no or little protections from its magnetic field. And the solar wind kind of incite the water component in the Martian atmosphere, accelerate all those waters in the Martian atmosphere to a very high speed, and eventually they got all blown away by the solar wind of the planet. So the light blue arrows in the slides in the figure shows water kind of escaping from the atmosphere of Mars. Next slide, please. So up to 70% of the early water of Mars could have been lost through atmospheric escape. However, this atmospheric loss, this mechanism itself cannot explain all the waters that have lost in the past. So there must be a different or alternative mechanisms that we could, through which Mars have lost its water. Next slide, please. So the second way to lose the water on Martian surface is to incorporate those early surface water into the crust. This is a relatively new theory scientists proposed for a water loss on Mars. We call this process serpentinization on Mars. So at suitable conditions, water in the middle, this water molecule would react with dry minerals on the Martian surface, like olivine, into a new mineral called serpentine that takes water into its structure. We call it serpentine because it literally looks like the skin of snakes. In this slide, I think I would just explain this image a little bit more. We have olivine, which is a common mineral that appears at the shallower part of the Martian surface, and the water molecules in the middle, and the combination of them will produce serpentine, which is shown on the left. We often find serpentine also at the bottom of the ocean in the Earth. That's also where water and the crust have a very intense interaction and a chemical reaction. Next slide, please. So some of the research, recent research suggests that if water had been leaking to the crust on Mars for billions of years, up to 99% of the Martian water would have been stored in the crust, actually, instead of being lost to the space. So surface liquid water became underground minerals that contains water in their structure, which is really interesting. The Martian science community is still kind of debating which mechanism, lost to space, lost to the crust, which one plays the most important role in terms of losing water, losing Martian water. The samples Perseverance rover now is collecting will help us kind of to settle this debate. Just to summarize kind of this part 2, how Mars lost its water, with few words, Mars was formed with wet materials, as Matt suggested. A significant amount of water was first stored in the interior of the planet, and soon after released to the surface through volcanic outgassings to form a liquid ocean, rivers or lakes billions of years ago. The majority of the surface, however, the majority of the surface water on Mars was lost to space or to the crust. The remainder of those water now becomes ice caps in the polar area of the Martian surface. This is kind of the short version how Mars got its water at the first place and then lost its water throughout its planetary evolution. Going back to the context of the talk, why do we care about water on Mars? Because water is like the nearest planet that potentially harbors life, and that can be explored by humans. So the history of water on Mars is particularly interesting. At the end of the day, perhaps we are more interested in life on Mars than water itself. So what do we know about life on Mars so far? I kind of summarize everything into like 4 bullet points. So far, we have no strong evidence of past or present life on the surface of Mars. And the surface of Mars today is not quite habitable, at least to human beings or any other animals that we really know of. The surface of ancient Mars had liquid water and may have been habitable for life. But I want to emphasize that habitable conditions with water do not necessarily mean it would just produce life. So the current answer is no. It may sound a little disappointing, but it didn't stop Martian science community and to like keep exploring the surface of Mars. There were a lot of unknowns about this neighboring planet, and we planned a lot of future missions, including possibly sending humans to Mars. So perhaps one of those future missions we planned or proposed might help us to find some evidence of life on Mars in a near future. Thank you. Any questions about the last part or the talk in general to me, to Matt? Do you have anything you want to say, Matt? I kind of just ended this talk with the part 3.
I mean, I guess I could just add another piece of context for why we think water on Mars is important, which is that water on Mars helps us elucidate water anywhere else in the universe. So we know the geology of the Earth very well. We know a little bit about how it formed. As I said, the only other rocks we have from any other planet are from Mars. And it's really the only other place where we've sent rovers, and it's a place where we've explored with orbiters most thoroughly. So if we can understand the difference between the formation of Earth and Mars, which are rather similar planets, but obviously one has water and one doesn't, if we can understand why that happened, it can help us build a more coherent picture of why water might exist on any given planet in the universe, or where it might be most likely to look for water-rich planets around other stars.
I have one question. If there's another from the crowd, I was wondering if you could explain a little bit why the Valles Marineris is so straight, especially like compared to things like the Grand Canyon.
I have an answer that JJ might not like. It's because it wasn't made by water. The canyons we find on Earth, and particularly the Grand Canyon, have like these meanders. So if you drew a river on a piece of paper, it would have that wiggly shape, because that's sort of just what water does when it's cutting through rock and sort of trying to get to the lower elevation. It's possible that Valles Marineris once contained water, but I think most people believe that it formed by some other non-aqueous and sort of non-water process. So perhaps there was some like localized rifting event or something of that nature. It could be like a stress fracture, because it's right next to those really big volcanoes that JJ was talking about. And that could split open the plateau in a more straight line, whereas if you're carving something with water, it tends not to make that shape.
Yeah, maybe I should just throw a few caveats there. All the geological features I was talking about, the northern basin, the various marineris, big canyons, there are also alternative theories about how they were formed without water. So I think it's more exciting to think they were formed by water, and if they were formed by water, we seem to have a coherent picture of why they were there. But they are not necessarily only formed by water. It could be a combination of both. So it's possible Valles Marineris was formed at first place through some rifting events, and then the glaciers, if the early Mars was cold, the glacier was on the southern highland, and then the climate changes, it started to melt, and then those water become liquid water and flow down into Valles Marineris to cover it into a much greater depth. So it could be a combination of a lot of factors. Their formation is not limited to like one time point. It's a continuous process. And it's also possible we don't have to fill up that type of features all the way to the top. We are not going to have that much water to fill up the entire canyon on Mars all in once. It's possible we carved this part of the canyon in this season, and then those waters evaporated into water vapor, and in a different season, it condensed again, become liquid water, and then carved a different section of the canyon. So there is this chronological component in the evolution of Martian surface. So many of those details are very unknown, and I think I should throw that caveat, just saying there's so much things we don't know about Mars, and there seems to be an emerging picture. But if we have a strong evidence in the past gathered by those rovers and missions, we can revise whatever we just talked about very easily because of the new evidence in the future.
Gotcha. We have one other question from our live stream on YouTube. They're asking, what types of experiments can you do to distinguish between the blue Mars versus the no water Mars of the past? The second part of the question is asking, how static is the surface of Mars?
Oh, I was muted, sorry. Can you repeat the first part of the question?
Yes, the first part is asking what types of experiments you can do to distinguish between the blue Mars versus the no water Mars of the past.
Experiment. Between blue Mars and red Mars, not blue Mars and snowball Mars.
Maybe they're looking for like a measurement, not necessarily something we would do in the lab.
Yes,
yeah.
The one way to do it is, as we see on Earth, all the shorelines has to be kind of relatively aligned with sea level, because of the gravity of the water. And the shorelines, if you get close to the shoreline, it doesn't matter if it's a Pacific shoreline or the Atlantic shoreline, the elevation is close to there. And the one way to test it is we go to the Martian orbiter data and look at those shorelines people have proposed are they relatively on the same level? Maybe they look like shorelines, but if you look at the elevation data, they are just so far apart, and they cannot be a coherent sets of shorelines. And in that case, maybe some part of those shorelines were formed by other mechanisms that actually not formed by water alone. So there's a way to test whether those shorelines are real or not real. If now those shorelines we tested afterwards and turns out those shorelines are actually not formed by water, in that case, maybe the early Mars was not blue at all. It was red all along, or it was more a snowball Mars. All the waters were located in the southern part and not the northern part. So I think there is a way to test that, and people actually have already reprocessing all the data as we collected and look at those shorelines in detail to see if they are actually shorelines and how much water they can contain. Maybe they're just small lakes and not the entire northern basin was once a single ocean. I think that was the biggest controversy in the field, whether the northern basin was a gigantic ocean or there were maybe one or two much smaller oceans or smaller ponds in the northern area. In that case, the Mars would have much less water in the past.
I guess I could do the second part of the question. The Martian surface today is very, very stable, especially in comparison to the Earth. So Earth, in the development of Earth's environment and the changes over time are due to essentially the presence of water. So that's like rain weathering the mountains and washing the sediment into the sea. The presence of life. So maybe forests colonizing a landscape and changing the sedimentation rate or something. And the presence of plate tectonics, which are the movement of plates which grind against each other or go down into the earth or split apart, causing volcanoes and earthquakes. None of those things exist on Mars. The last volcanic eruption on Mars was a very long time ago. Mars has never had any plate tectonics, so it really never had the sort of very dynamic, constantly renewed surface environment that the Earth does, which is why you see like craters on Mars that are probably billions of years old, where they would have been quickly erased on Earth. However, it's not entirely static. So InSight, which is the seismic lander that went to Mars a couple of years ago, has detected a few Mars quakes, which are not very big, but they're appreciably large enough to be measurable. So this means that there's some at least settling or restructuring of the Martian crust at the present, but it's nothing compared to what we see on Earth.
Great, and we did get a reply from the question asker saying that's exactly what they were curious about, and saying thank you for the response. Are there any other questions? All right, well, thank you very much to our speakers. I definitely learned a lot. Thanks for taking the time to put this together for us and for sharing the work that you're doing. As a reminder, our next seminar will be in 2 weeks on April 20th. So we hope to see you then, and thanks again.
Yeah. Thank you so much.
Thanks for listening, everybody.
Thank you. Why you are still here, Matt?
What do you mean? I feel like we should stay at least until everybody else leaves.
Are we going to talk about something, or?
Well, I'm pretty sure we're still being broadcast to YouTube, so I would refrain from discussing anything of particular import or sensitivity.
I see.
I just wanted to make sure that everybody left before we left.
Thank you, Maggie and Sebastian.